Okay, so today we're talking about linear regression analysis. So what's going on over here? So basically, linear regression analysis is analysis of paired data. Normally, in a stats problem, you're going to take a sample, you're going to ask everybody a question. They're going to give you an answer like, how old are you? You're going to ask that, for example. Everyone's going to give you one number. But for linear regression analysis, instead, we're going to ask everybody in our sample two questions. We're going to get two numbers from everyone, and we kind of want to study the relationship between those two quantities. So, for example, it could be, so let me give you an example of two quantities that are related to each other somehow, like the amount of time you study for a class and your grade in the class kind of thing. So like, when one of them is higher, like if you study more, then your grade is usually higher kind of thing. Another example is height and shoe size. You may have heard of that one before. In general, taller people have bigger shoe sizes kind of thing. So those two quantities, your height and your shoe size, they depend on each other. I'm not saying every time a person's taller, they always have bigger feet kind of thing, but in general, that's the case. Not always, but like on average kind of thing, that's the case. So if you want to study, like let's say we want to study the relationship between height. So height is what quantity and shoe size is another quantity. What you would do is you would take a sample and you take a bunch of people and you'd ask everybody two questions. You would say, okay, tell me your height and tell me your shoe size. So let's say one person, I asked them, what's your shoe size and then what's your height? And let's say the person says, I know the shoe size depend on if you're male or female. So maybe just to make it easier, we only talk to males. Or even if we talk to females, we're going to ask, what's your shoe size in a male shoe kind of thing? I don't know. But let's say the person says, my shoe size is 9.5. Okay. And then I ask, okay, now how tall are you? And the person says, I'm 67 inches tall, which is 5'7". Okay. What I do is I take the two numbers and I make a point out of it. Plotting points, like in some algebra class in the past, you had to plot a point. Like they would say plot the point 3,5, and you would draw like two numbered lines, and then you would go, you would start here and you would go 3 this way and then 5 this way, and then you put a dot. So that dot right there is the 0.35. Okay, so that's what I'm saying. I'm saying take the two numbers you got from that one person, make a point out of it. This is normally how we write it, parentheses, comma in the middle, and then you plot that dot. You plot a point. Every person in your sample is going to give you two numbers. That means every person in your sample is going to give you 1 point. Let's say I talk to another person, I say, what's your shoe size? And they say, I'm size 11. And I go, how tall are you? And they say, I'm 74 inches tall, kind of thing. So now we have another point. That one person gave me two numbers, the two numbers whose relationship I'm studying, height and shoe size, and I make a point out of it, and then we can plot it. If I do this for, like 20 people, I would get 20 points. I'd get 40 numbers because I get 20 pairs of, I'd get a pair of numbers from each person, so I'd get 20 pairs of numbers, but it would give me 20 points, and I could plot those 20 points in the end. And I would get a graph that looks something like that. This is called a scatter plot. It just means you plotted a bunch of points. Okay, and the scatter plot, you look at it, and because you see that it looks like the data is going upward, okay, what that basically tells us is when one of the quantities increases, so does the other one. So if the height of the person is bigger, the shoe size is bigger, or the other way around. If the shoe size is bigger, then the height is bigger, kind of thing. So it kind of lets me know the relationship between those two quantities. Now you might wonder, why did I put shoe size for the first coordinate, for what we call the x coordinate? Why did I put the height for the second coordinate, the y coordinate? Well, at some point in the problem, they're going to say, make a prediction. They're going to say, okay, you have this scatter plot, and now somebody walks into the room and their shoe size is this, guess their height, predict their height. Whatever they ask you to predict, that we're always going to make y. So if I make the heights of the people y, then that means at some point in the problem, they're going to say, here's the person's shoe size, predict their height. Whatever you're predicting, that's y. So that's the reason I put height as the y coordinate. Pretend in this example that we want to predict the person's height. They tell us their shoe size and we want to predict the height. If we wanted to predict the shoe size, if someone says, here's how tall I am, guess my shoe size, then I would make shoe size the y coordinates. Okay, just so you know. Whatever we're trying to predict, we make the y coordinates. Okay, so if we want to investigate the relationship between height and shoe size, again, we ask everybody 2 questions. We say, tell me your height, tell me your shoe size. We make a point out of each person's pair of answers. We'll put shoe size first and height second, because if we want to predict the height at some point, you do this for all sorts of people, and you get a scatter plot. You just plot a bunch of dots. Then what you do is you find the equation of the line that's as close as possible to all the data. This is called linear regression analysis. The word linear has the word line in there. What that means is every problem in this section, we expect the scatter plot to look like a straight line of dots, or at least close to a straight line of dots. We expect it to form a line. We don't expect it to form like a different shape. It's a line, but it might not be perfect. So instead of just going straight up like this or straight down, it might be like, trying to go up, but the dots are not exactly going straight up, or they might be going down, but not exactly straight down. That's why we call it a scatter plot. But we expect the data to form a line. And if you look at this data, you cannot draw one line that goes through all the dots. It's not possible. The dots do not line up on a straight line. So what we're going to do is we're going to find a line that's as close as possible to the data. That's this line in this picture over here. You find the equation of that line, and then you use the equation to make your prediction. And that's basically the end of the story. Whenever you've learned about lines before, you probably learned that their equations are like y equal mx plus b, where m and b are numbers. So what you'll do is you find the equation of this line. I'm just going to make up an equation right now. Let's say the equation of the line is 6x plus 10. Okay. Or let's make it plus 8. Okay, 6x plus 8. I just made this up at random, okay? Let's say we're studying height versus shoe size. We plot all these points, and we get this is the equation of the line. Then you can make a prediction. You can say, okay, somebody walks in the room and their shoe size is 9. So the shoe size is 9. Guess the height. Well, if you're telling me the shoe size, you're telling me x. You just plug in 9 for that x, and you guess the height. So it'd be 6 times 9 plus 8, 6, 48, 54, 64, 62, and you get 62 inches, which is 5'2". So that would be our guess. So once you have the equation of the line, this is the line that's as close as possible to the dots in your scatter plot. Then you plug in the x that they give you, and you can predict the height. So my guess is that the person would be 5'2". I mean, I'm wrong. I might be wrong, but that's my guess. That's what linear regression analysis is. So now that I've told you the story, we're going to do 2 examples. The first one we're going to do is going to be done very fast, just like this one here. I'm going to do it very fast just so you get the big picture of what the story is. And then I will go into things a little bit in little detail. And then we'll do another problem a little slower, and then that'll be the end of the story for the day. So here we go. Let's take a look at this example. The chirp rate of crickets is strongly correlated with the outside temperature. So in case you didn't, you may have known that already. If you didn't know that, it turns out that the hotter it is outside, the faster crickets chirp. The colder it is, the slower they chirp. So they're related. Those are the 2 quantities. The chirp rate of crickets and the outside temperature. Those are the 2 quantities that we're trying to study the relationship between those 2 things. So it says on 8 different days, the statistician went outside and measured 2 quantities, the number of chirps a cricket made in a minute and the outside temperature. They called the number of chirps for the cricket X and the outside temperature Y, and then we have this data over here. The fact that they made the chirp rate of the crickets X and the outside temperature Y, what that means is at some point in the problem, they're going to ask you to predict the outside temperature, because you always predict Y. And if you look right here, it says predict the outside temperature. Okay, so that's why they made the outside temperature Y and the chirp rate X. So if you look over here, this is on 1 day. The statistician went outside, heard a cricket chirping. It was chirping 88 times a minute. And then the statistician measured the temperature. So he measured 2 things. And the temperature outside was 69.7 degrees Fahrenheit. Then on a different day, so here's a different day, statistician went outside and heard a cricket chirping 118 times a minute, and the temperature outside was 93.3 degrees. And we have 8 pairs of numbers for the 8 days the statistician went outside. So every day he went outside and got 2 numbers. And what we do is we're going to take these pairs of numbers and we're going to make a point out of it. So this first pair of numbers, we're going to think of that as the point 88, 69.7, and we're going to plot that point. Then here's another point. 118 is the x coordinate, 93.3 is the y coordinate. We're going to plot that point. We're going to do that for all 8 of these, and we're going to get a scatter plot with 8 points in it. Now, I'm not going to ever make you make a scatter plot because that's kind of annoying to sit there and plot points. Okay, so you don't have to do that. But for these 2 examples, I will show you the scatter plot so you understand what's going on. But when I ask you a question, a linear regression analysis question, I'm always going to ask you these 4 questions. Okay, so for this example and then the one we do later, these are the 4 things I'm going to ask you. So be prepared to do these 4 things. The first thing it says, find the linear correlation coefficient R. Okay, let me talk about this briefly. R is a number that you can calculate from this data. So R is a number. And what's the usefulness of this number? It has a lot of uses, but we're only going to use it for one thing because it's the last day of class. I can't teach you any other things. But R will let me know how close to a straight line the data is. So if I was to plot these points, which again, I'm not going to have you plot them, but if you did plot them, this R will let me know, does it look really close to a line? Is it really far from a line kind of thing? Some things to know about R. R is always between -1 and 1. Okay, so between -1 and 1. If R is positive, then the data goes upward. Okay. If R is negative, then the data goes downward. Okay. If R is exactly 1, then the dots not only, so it's positive, so they're going to go upward. But if it's exactly 1, then it's going to go, the dots are going to form a perfect straight line. They're going to be lined up, no scatter at all. But if R is a little bit less than 1, like 0.9 or 0.8, then it'll look like this. It'll look close to a line, but there's going to be some scatter. Some dots are going to be off. So if it's close to 1 but not 1, we expect this. If it's exactly 1, we expect something like that. If R is -1 exactly, because it's negative, it's going to go down. But if it's -1, then the dots are going to go down and line up perfectly in a straight line. Okay. But if R is close to -1, then we expect it to look close to a straight line going downward, but a little bit of scattered like this. So again, if it's -0.9 or -0.8, then we expect something like this. Otherwise, if R is close to 0, then it means the data doesn't really look like a straight line. At least that's the story with R. Okay, you calculate R from this, and it gives you an idea of what your scatter plot looks like. We'll talk more about it later. Then the next question is find the equation of the least squares regression line. Okay, so remember, it turns out that any scatter plot, if you, again, I'm not going to have you make a scatter plot, but if you were to make it, there's a line that's as close as possible to the data, whatever that means. We'll talk about what that means in a minute. But what you want to do is, once you have your scatter plot, once you have your data, you want to find the line that's as close as possible to the data. It's called the least squares regression line. And then you're going to use that line to make a prediction. Once you have the equation, then you can make a prediction. Part C says, predict the outside temperature. Again, that's Y. If you hear a cricket chirping 140 times per minute, that's X. So they're telling you X is 140. You're going to plug that into the equation of the line, and you're going to calculate Y, and you're going to make your guess for the outside temperature. And then the last thing, which is probably the hardest thing, this is confidence interval stuff. We've done this before in chapter 9. Once you predict the outside temperature, you're just going to get a 1-number guess when you're done with part C. We don't want a 1-number guess because we're probably going to be wrong. If you say, I think the outside temperature is, 93 degrees, and it's 94 degrees, you're wrong. We don't want to be wrong. So part D says, find a prediction interval. It's basically saying, take your 1-number prediction from part C and build a confidence interval around it. And the way you do that is you're going to add and subtract the margin of error, just like we did in chapter 9. Okay, let's go through each of these parts here. Let's not worry about those 2 things. But here's a scatter plot. If you were to plot the points, this is what it looks like. So real quick, tell me, do you think R in this problem is positive or negative? What do you guys think?
Positive.
Positive, yeah, because the data is going upward. Okay, so expect R to be positive, and I'll show you how to calculate it later, but I calculated it, and it turns out R is 0.8693. We didn't expect it to be exactly 1 because the dots are not lined up perfectly, but somewhat close to 1 because it looks kind of close to a line, just some of the dots are off a little bit. So positive and somewhat close to 1. Again, I'll show you how to calculate the R later. In this first example, I'm just going to do it really fast. Okay, then the second question said, find the equation of the least squares regression line, the line that's as close as possible to the data. That's drawn in the picture there. Okay, so we got to find the equation of that line. Again, I'll show you how to find the equation later. I'm just going to give you the equation right now. The equation is this. It always looks like y equals a number times x plus a number. Okay, it's, you know, that's what it means when it's y equals mx plus b. The m and the b are numbers, and the x and the y have to be in the equation. You might say, Greg, why is it y hat instead of a y? The reason is because y is what we're trying to predict. Y hat is my best guess for y. Just like back in chapter 9, when we're trying to guess percentages, p, our best guess for p was p hat kind of thing. So p hat is like my guess for p, but p is what I want to know. Y hat is my guess for y, but y is what I want to know. So that's why they write a y hat. Your best guess is, you know, use this thing. Part C of the problem said, if a cricket is chirping 140 times per minute, again, that's x, what's the outside temperature? All you do is you take the 140 and you plug it into your line equation for x, and you calculate. And because it's 0.52 whatever, and then there's an x next to it, that means multiply. So you got to do 0.5236 times 140 plus this, and that's your guess for the outside temperature. So if you plug it in, plug in the 140 for the x and calculate, you're guessing that if you went outside and heard a cricket chirping 140 times a minute, you're guessing the outside temperature is going to be 101 degrees. Okay, so we made a guess. And that would be the end of the story, except what if it's not exactly 101 degrees? We want to have a correct guess. So now what you need to do is you're going to build a confidence interval around your guess. We don't want a one number guess, we want a confidence interval. Part D said find a 95%. So in chapter 9, we call them confidence intervals, but in this section, we call them prediction intervals, but it's basically the same thing. We're looking for a 95% prediction interval. So you have to calculate the margin of error. Again, I'll show you how to calculate it later, but it turns out for this problem with this data and this confidence level, this is the margin of error. And now how do you build your interval? Well, you take your best one number guess, y hat, and you add and subtract the margin of error, just like we did back in chapter 9. So you're going to do 101 minus 15.9, that gives you this number. You're going to do 101 plus 15.9, that gives you this number. And you say, I think the outside temperature is somewhere between here and here. And that's the end of the story. So that's the kind of problem that I will ask you in the linear regression problem. All right, now again, I know I haven't showed you how to calculate anything yet. We'll talk about it. But as far as the big picture goes, any questions? Okay, sounds good. So what I'm going to do now is I'm going to go through each of the little parts of the linear regression problem, and we'll just talk about it in a little more detail. All right, so let's talk about the linear correlation coefficient for R first. I really told you pretty much everything there is to tell you about R already, but let me go ahead and just tell you again. So R is a number. Okay, linear correlation coefficient R, it's a number. It can be calculated from the paired data, from the data we have, and it tells you how close to a straight line the data is. So it measures how close to a straight line the data is. It's always going to be between -1 and 1. If it's 1 or -1, the data is going to form a perfect straight line. If it's 1, it's going to be a perfect straight line going upward. If it's -1, it's going to be a perfect straight line going downward. If it's close to 1 or -1, the data is going to look almost like a straight line, but a little scattered. So in R close to 1 will look something like that. The data is going to go up and it's going to look somewhat close to a line, but a little bit of scatter. If R is close to -1, but not exactly -1, it's going to look like this, you know, where the dots are trending downward and it doesn't exactly look like a straight line, but pretty close if it's close to -1. But the further R gets from -1 and 1, or the closer it gets to 0, the less it's going to look like a line. It's not going to look like a line anymore. Remember, R, here's a number line. Here's -1, here's 1. If R is 1, again, it's a -1, it's a perfect straight line going downward. If R is +1, it's a perfect straight line going upward. If R is somewhat close to -1, it's going to look something close to a straight line going downward. If it's close to 1, it's going to look like a close to a straight line going upward with some scatter. But 0 is right here in the middle. So the closer we get to 0, if R is pretty close to 0, what that means is the data doesn't look like a straight line anymore. Because it's called the linear correlation. We're measuring how close to a line is the data. So if it's close to 0, what that means is either the data will be scattered all over the place, okay? Or it could form a neat shape. When I say neat shape, I don't mean like neat, cool guys, you know what I mean, like that. I mean it could form a clean shape, just not a line. So like, for example, if you look at this data, it looks like it's following some curve, but that curve is not a line, okay? So either the dots are just all over the place, or, you know, so like it's really sloppy, the dots are everywhere, or the dots can form a nice shape with no scatter at all, but it's not forming a line. If it doesn't look like a line, then the R is going to be close to 0. Here it says if R is positive, the data trends upward. And what that means is when one quantity increases, so does the other one. So if X increases, so does Y. That also means the slope of the line is positive. If you don't know what the slope of a line is, don't worry about it. But if you do know, then if the slope of the line is positive, it means the data is going upward. So if R is positive, so is the slope, but R and the slope are not the same because slopes of lines can be bigger than 1, but R can't be bigger than 1. Okay, but if the data goes upward, R is positive, and also the slope of the line is positive. If R is negative, the data is trending downward. What that means is when one quantity increases, the other one decreases. So if X increases, Y decreases. It also means the slope of the line is negative. So again, I already told you that, but I told you that again. And then let's take a look at these examples real quick. Here's a scatter plot. Do you think R is positive or negative? What do you guys think?
Positive.
Positive, yeah. Data's going up. Do you think it's exactly 1 or close to 1, or what do you think? So the answer is the R in this problem is exactly 1 because the dots are lined up perfectly, or at least that's what I tried to draw. You could draw a line that goes through all the dots. So R is exactly 1 over here. So it's positive. Again, that's what happens when the data is trending upward. Again, that means when one quantity increases, so does the other one. And R is exactly 1 over here. Okay, here's another one. So R positive or negative?
Positive? Is it positive or negative?
Yeah, R is positive again because the data is trending upward again. So R is positive. When X increases, so does Y. But this time R is not 1 because the dots are not lined up perfectly, but it's going to be something close to 1. Now, again, I still haven't shown you how to calculate R, but I have the data for this, and I calculated the R for this. And it turns out that it's 0.9698. So it makes sense. It's a positive number, and it's pretty close to 1 because the data is trending upward, and it looks close to a straight line, just a little bit of the dots. Some of the dots are off a little bit, so just a little bit of scatter. Let's go to this one. R positive or negative? What do you think?
Negative?
Negative. Yeah, R is negative because the data is trending downward. Do you think it's exactly -1 or close to -1? So again, the way I intended to draw this one is for the dots to line up perfectly. So you can draw one line.
Oh, okay.
All the data. So what is it? Tell me. R is what?
Exactly.
Right. Okay, so R is exactly -1 in this picture. Okay, for this one, the data is trending downward. That means R is negative again. R is not exactly -1 here because the dots are not lined up perfectly on a straight line. And there's a lot more scattered than the other one. So I expect R to be pretty close to -1, but maybe not as close as that one that I showed you on the other slide over here. I calculated the R for this one. It turns out the R is -0.77. Again, the negative tells me the data is trending downward, but it's not super close to -1. It's -0.7 something. The fact that it's kind of close to -1, but not too close, means there's a lot of scatter in the data. So it's like a line with a lot of scatter. So the dots are not lined up that well, kind of thing. Here's another one. In this example, I don't really see a trend. It doesn't look like it's going up or down. The dots are just kind of all over the place. When that happens, the R is going to be close to 0. So I expect R to be close to 0. When X increases, what happens to Y? I don't know. It goes all over the place. Just goes up, goes down, whatever. There's no clear trend there. Okay, so that's an example when R is close to 0, and I calculated the R for this data, and it turns out to be -0.1010. Again, pretty close to 0. So that's one time where the R can be close to 0, if the dots are all over the place. Another time is if the dots line up on a curve, but not a straight line. So in this example, I intended to draw dots that line up on a parabola. So there's a parabola you can draw that goes through all these dots. So the dots line up on a parabola, but then R measures how close to a line is the data. So again, R is going to be close to 0. Also, if I ask you, is the data going upward or downward? It's not clear. It's going upward for a little, then downward for a little. So lines can't do that. Lines either just go upward or they go downward. They can't go up and then back down. That's not a line. So that means R is going to be close to 0. So I expect R to be close to 0 again. When X increases, what happens to Y? I don't know. It goes up and then it goes down, you know. So, and then I calculated the R for this one and it turned out to be positive 0.1183. Again, pretty close to 0. So just looking at the R lets me know not that close to a line. Whatever the scatter plot looks like doesn't really look like a line. But if it's close to 1 or close to -1, then the dots look like a line with a little bit of scatter. That's the idea. Now, how do you calculate R? There's not really much to tell you. Here's the formula. Now, some of the formulas we're going to see today are kind of nasty, but don't worry, they're not that bad. But that is the formula for calculating R, and we'll look at it again when we look at the next example. All right, so that's the story with R. Now, the next thing we need to talk about is the least squares regression line. That's the line that's as close as possible to the data. So I want to talk about what that means a little bit more. Okay, so it says the goal is we want to find a line that's as close as possible to all the data points. Once in a while, you can draw a line through all of them, and then that's the line that we're looking for. But if you can't draw a line that hits every point, we're looking for a line that's as close as possible to all the points. I want to talk about what that means. So every line, once you have your scatter plot, any line you draw has a total error, and we're looking for the line with the smallest total error. So I want to talk about what this means. So here's some data, just 3 dots there. And I made up 2 lines, just made them up at random. Y equal -2x plus 13, y equal positive 2x plus 2. And I just want to know which of those 2 lines is closer to the data so we can understand what that means. So let's look at the first line. So the 3 dots here, okay, is a scatter plot. It's when you plot these 3 points. Okay. And then I graphed this line in red, so it's over here. Okay. I want you to notice none of the blue dots are on the line. So each dot has an error, like how far is it from the line vertically, okay? So for the first blue dot, the error is how far is it vertically from the line? I want to know how long that black line segment is. And you can do this real easily because if you look on the y-axis here, each of these lines is 2 apart. And what that means is if you go from one of these lines to the middle, it's 1 apart. From the middle to the next line, it's 1 apart. Or if you just go from here to here, it's 2, here to here, it's 2 kind of thing. So if I just want to know how far apart the blue and the red are, if I go from here, let me draw the line right on the blue dot. So from here to here, that's 2 apart. From there to there is another 2. From there to there is another 2. And from there to there is another 2. So the first dot is 8 lower than the line. So the first error, error 1, the error in the first point is 8. Actually, the error in the first point is -8. If the dot is below the line, we're going to say the error is negative. If the dot is above the line, then the error is positive. So the first error, don't worry about that calculation there, but the first error is -8. Now let's go to the second dot. Here's the second blue dot. And I want to know how far is it vertically from the line. Go straight down or up to the line. And to figure out this error, you just go, so from here to here is 2, here to here is 2, here to here is 2. That error is 6. So the blue dot is 6 away from the line if you measure vertically. And there's +6 because that dot is above the line. So the second dot has an error of 6, or the line is 6 away from the dot. When you go to the third dot, same idea. It's not on the line, so I want to know what the error is. How far vertically are those 2 dots? So again, just go from here to here, that's 2, there to there, that's another 2. That error is 4. So if you have 8 dots, there's 8 errors. In this case, we have 3 dots, we have 3 errors. And now I want to calculate the total error. What is the total error? How should we calculate the total error? The word total means add. So you might think, let's just add these and we'll get the total error. So that's the first thing. Should we just add the errors? And the answer is no, because we don't want the negatives and the positives to cancel out. We saw the same thing happen to us in this class, the second day of class, when we're talking about standard deviation. We had some negative and positive standard deviations, and when we added them, we got 0. And so we don't want the negatives and positives to cancel out, because if negatives and positives cancel out, it's going to make the line seem like it has less error than it has. So we want to get rid of the negatives. Okay, so that's the idea. We don't want the negatives and positives to cancel out, so we have to come up with an idea of how to get rid of the negatives. And again, similar to what we did second day of class when I taught standard deviation, the next idea would be to take the absolute value of each one. So maybe the total error, we're trying to define what total error is, okay? How should we find the total error? Should we take the absolute value of each of these and then add them is the question. Now that's the one that makes the most sense. If you don't want the negatives and positives to cancel, erase all the negatives and then add them, and that'll be the total error. Sounds great, but we're not going to do it that way. The reason is because absolute values suck. That's the right answer. In math, absolute values suck. They're not easy to work with. Just like in the second day of class, we didn't use absolute values to get rid of the negatives because they're just hard to work with. So what are we going to do instead? We had to come up with a more creative way of getting rid of negatives other than using absolute values. And the answer was to square each of them. So the total error in this line, the way you find it, is you square each of these errors and then add them. And that, whatever number you get, is a measure of how close the line is to the data. Okay, and again, we're squaring because when you square, you get rid of the negative. So what is the total error? You have to square this, and add them. So you can do -8 squared plus 6 squared plus 4 squared, you get 116. This number 116 is the total error of this line. It's measuring how far is the line from the data. Okay, now we're going to do this for the other line that I made up. So again, we have the same 3 blue dots, but this time I'm drawing the line y equal to x plus 2. It's drawn there. And I want to know what's the total error for this line. Again, notice none of the blue dots are on the line. So I want to know, like, what's the distance between this blue dot and this red dot over here? That's going to be called error 1. They're just 1 away because the distance from here to here is 1. Okay, so distance from the middle to one of those black lines there is 1. So the first error is 1. Actually, the first error is -1 because the blue dot is below the line. So first error is -1. Again, don't worry about this. For the second one, how far is this blue dot from this red dot? Well, again, if you go from here to here, that's 2. From there to there, that's 2 more. And there to there, that's 1. So 2, 2, and 1, that's 5. So the second error is 5. And it's +5 because the blue dot is above the line. For the third blue dot, it's not on the line. How far is it from the line vertically? It's 1 away. That error is 1. Technically, it's -1. And now we're going to find the total error for this line. Again, how do you find the total error? You square each of these and add them. So you can do -1 squared plus 5 squared plus -1 squared, and you get 27. This 27 is a measure of how close this line is to these data points. Okay, so between these two lines, which one would you say is closer to the data? The one that has an error of 116 or the one that has an error of 27? Which one is closer to the data? Yeah, the one that has error 27. That means this line here on the right is closer to the data than this one. So we don't like this line. This one's closer to the data. Yeah, okay. So that's what it says over here. So line 2x plus 2 is closer to the data because the total error is smaller. But that doesn't mean that's the closest line to the data. I just wanted to explain to you, what does it mean for a line to be close to the data? Okay, so it's closer if the total error is less, the way we define the total error. Now the question is, can we find a line that's closer to the data than this one? Is it possible? The answer is yes. And it's actually a calculus question. So I want you to know that in a calculus class, one of the big topics is called optimization, which is finding the smallest or largest of something. We're looking for the line that has the smallest total error. Okay, so it can be done. It's a Calc 3 problem. We're not going to do the calculus. We're just going to steal the formula from the calculus results. So if you do the problem in calculus, whatever the formula turns out to be, we're just going to steal it and use it. So it turns out that if you have any set of paired data, there's a line that's closer to the data than any other line. And that line is called the least squares regression line. So that's the line that we want. So what it means, once we find this equation, any other line will be further away from the data than this one. It's called least squares because of the way we define the total error. Remember how we found the total error? We squared each error and then added them. So that's why it says squares. And then we want the least, the one that has the least of this total error. Okay, so I'm just going to give you the formula now. So what's the formula for it? Well, normally for a line we write y equal mx plus b. But I don't know, for some reason, the number that's in front of the x, instead of them calling it m, they call it b1. Just remember that b1 is the number that's in front of the x, and the number that's added at the end there is called b0. And here's the formula for b1 from calculus, and here's the formula for b0 from calculus. Again, we'll talk about calculating it later, but we have formulas for it. So you just take your paired data, calculate these things, and then you have the equation of your line. Okay, and we'll talk more about this when we do the next example. After you have the equation of the line, you can use the line to make a prediction. That was part C, right? Use your equation of your line to make a prediction. Great. And that's real easy. You just plug in the x number they give you into your line equation and you get your prediction. But remember, we don't like one number predictions. We want an interval prediction instead of a one number prediction. We want a confidence interval, and that makes it more work. So y hat is our best guess for y. So y is what we're trying to predict. Y hat is our best guess for it, but it's a point estimate, so it's almost always wrong. So instead we want an interval estimate, but again, we're not going to call them confidence intervals in this section, we're going to call them prediction intervals. And basically what you're going to do is I'm going to give you a formula for the margin of error, and what you do is you take your best one number guess, y hat, and subtract the margin of error. Then you take your best one number guess and add the margin of error and say, the number you're trying to predict for y is between these two numbers. And here is a slide with all the formulas on it. So I already showed you everything above that line, but if you look below the line, this is the formula for the margin of error. Don't be too scared of it. We'll do an example in a minute. Some things to tell you though. First of all, there's a T alpha over 2 over here. You know, when we did confidence intervals in chapter 9, we looked for Z alpha over 2, T alpha over 2. So just so you know, in this section, it's the T distribution that you're going to be using. You need to look up T alpha over 2 the way we did back then. The degrees of freedom formula is n minus 2, which is a little weird. Usually it's n minus 1, but in this section it's n minus 2. And be careful on what n is. Sometimes students get that wrong. N is how many pairs of data you have. So if you talk to like 7 people, each person's going to give you 2 numbers. You're going to have 14 numbers, but n is not 14. It's how many pairs of numbers you have. You have 7 pairs of numbers. So just keep that in mind. N is how many pairs of numbers you have. And then there's this other thing in this margin of error formula, SE over here, and the formula for that is this mess over here. There's a name for that. That's called standard error of estimate. It's a weird name. You don't need to remember it. But long story short, when you're calculating the margin of error, you're going to have to find T alpha over 2. You're going to have to find SE. You're going to put that over there. And then you multiply it all together. T alpha over 2 times SE times this root in any way. Then you have your margin of error. And then you add and subtract it from your y hat, and you got your interval. All right. So again, now the story is completely over. Now we just have to do an example so you see how it all works. So again, it might be a little too early, but does anyone have any questions so far? All right, sounds great. Let's go and see what an example is going to look like. Again, I'm not really going to write anything down. I calculated everything for you. So just pay attention. You don't have to sit there and calculate anything. But when the lecture's over, you should recalculate things to make sure you're able to calculate them on your own. All right, here we go. So it says, in order to study global warming, the data below was taken over different years. Carbon dioxide levels are in parts per million and temperatures in degrees Celsius. So what that means is in one year, they measured the carbon dioxide level in the air, and it was 314 parts per million. And that year, the average temperature of the Earth was 13.9 degrees Celsius. So in that year, we got those 2 numbers, a pair of numbers there. In a different year, the amount of carbon dioxide in the air was 317 parts per million, and the average temperature of the Earth, 14 degrees Celsius. So every year we get a pair of numbers. Okay, so what's the carbon dioxide level in the air, and what is the average temperature of the Earth? And we're trying to see if these two quantities are related to each other, kind of thing. All right, and then, well, let me say this. Notice that they put temperature as y. What that means is at some point in the problem, they're going to ask you to predict the temperature, like they say over here. They're going to basically say, I'm going to give you the carbon dioxide level, predict the temperature of the Earth that year, kind of thing. Also, make sure you understand, if I ask you what n is, you don't count all the numbers total. You have to count how many pairs of numbers you have. So there's 1 pair, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is 10 in this problem. It's a very common mistake for people to think it's 20. So just make sure you understand. It's not how many numbers you have total. It's how many pairs of numbers you have. So we have 10 pairs. That's what n is. Okay, and I'm asking you these 4 questions. First one says, find the linear correlation coefficient R. Find the equation of the line that's as close as possible to the data. Use your line to make a prediction. It says, find the temperature of the Earth or predict the temperature of the Earth if the carbon dioxide level reaches 400 parts per million. So there's no 400 over here. But they're basically saying, if the pollution, the amount of carbon dioxide in the air gets to 400, then you predict what the average temperature of the Earth would be. Okay, so that's what part C says. And then that's, of course, a 1 number guess. So now we want an interval guess, and the way to get an interval guess, well, that's what part D says. Construct a 90% prediction interval for the temperature of the Earth if the carbon dioxide level reaches 400 parts per million. Okay, so when you're doing a linear regression problem, really good advice. Before you do the problem, you want to calculate these 6 quantities. Okay, so let's go ahead and go through what those mean. Let's go with the first one, sum of x. Okay, sum of x, what does that mean? It means add all the x numbers. These are all the x numbers. You just add only the numbers in the first row there. So you can do 314 plus 317 up to 369. I did it already. The answer is 3377. So I'm going to go through this pretty fast because I've already calculated it for you, but just make sure you understand what you need to do to calculate them. So sum of x means just add the x numbers, add the top numbers. Then you're going to do the same, then you're going to find sum of x squared. What does that mean? That means you're going to square each of the x numbers and add them. We're not even looking at the bottom row, we're just looking at the x row. So you can do 314 squared plus 317 squared all the way up to 369 squared. And then you're going to add all those up. The answer to that is this messy number over here. After you do that, you're going to do the exact same thing for the y's. So now you're going to find sum of y. What does that mean? That means add all the y numbers, just the y numbers. So you're going to do 13.9 plus 14 all the way up to the 14.4. Here's the answer to that. Then you're going to find sum of y squared. Again, what that means is you're going to square each of the y coordinates, so all the way up to this one, and add them up. So you can do 13.9 squared plus 14 squared all the way up to 14.4 squared. Add them up, you get that. Okay, after you find these 4 things, then you're going to find sum of xy. When you have letters next to each other, it means multiply. X times y. What that means is for every point or for every pair of numbers, you're going to multiply x times y, and then you're going to add them. So you're going to multiply these 2 together. Then you're going to multiply those 2 together, then multiply those 2 together, and go all the way down until you multiply those 2 together. Then you add them up. Remember, this symbol means add. So you're going to first do 314 times 13.9 plus 317 times 14 plus, and you do it for every pair, up to 369 times 14.4. When you're done with that, there's the answer. And then the last thing you're going to do is you're going to calculate x bar. Remember, the bar on top of a letter means average, but this means just find the average of the x's. So you're just going to find the average of these numbers. So you're going to add them up and divide by how many you have. We already added them up over here. Okay, so you add them up and then divide by how many you have. And again, n is 10. Sum of x was 3377, so you add them up, divide by 10, and there's the answer to that. Don't find y bar. Don't find the average of the y's because I don't need that. It doesn't appear in any formula that we're going to have. Okay, so in any linear regression problem, calculate these 6 quantities first, and then because you'll need them in all the formulas that we're going to see. Okay, now remember part A was calculate R. Before we calculate R, here's the graph of the data. So this is a graph of the data just so you know, you don't have to draw any graphs, okay? But I'm drawing it for you because I can, and it takes a second. So there's the graph of the data. And from the data, you tell me, do you think R in this problem is positive or negative? Just positive or negative, what do you think?
Positive.
Positive, yeah, because the data is trending upward. Do you think it's exactly 1?
No.
No, because the dots aren't lined up perfectly. So, but I do expect it to be somewhat close to 1. It's kind of like a line, but there's some scatter. Okay, so yeah, we expect it to be positive. When x increases, y increases. We expect it to be somewhat close to 1. Here's the formula for r. Now take a look at the formula. Everything in the formula has to do with the things I asked you to calculate already. Remember, n is 10. Sum of x, y, you calculated that at the beginning. Sum of x, sum of y, you calculated that at the beginning. Sum of x squared, sum of x. So all these quantities you calculated at the beginning, all you do is fill it into the formula now. Okay, so just plug in all the numbers that you calculated already. This is what you would get. And when you calculate that whole mess out, you're going to get 0.8920. So as far as me explaining it to you, that's all there is to tell you. You just fill into the formula and calculate it. But you just want to, on your own, when you have more time, so after class or whatever, try to calculate this on a calculator. And if you got this number, then you're calculating it right. And one time in this class, we calculated something that had 2 roots on the bottom. And what I told you to do was divide by the first root, get the answer, and then divide by the second root. So if you remember that trick, that's a good trick to use for this R business over here. And again, take a look at the R. It's positive like we expected, and it's kind of close to 1. It's 0.89, pretty close to 1. Okay, so that's how you do part A. Then part B said, find the equation of the line, the equation of the least squares regression line, the line that's as close as possible to the data. In order to find the equation of the line, you got to find B1 and B0. B1 is the number that goes in front of the X, and B0 is the other number that's added at the end. Well, here's the formula for B1. Again, take a look at the formula. It has all those quantities I had you calculate earlier. It has sum of x, sum of xy, sum of x, sum of y, sum of x squared. So, and then n is 10. Just fill into this formula with the stuff we calculated earlier. Calculate that mess, and you get 0.0109. This is the number that goes in front of the x in the equation of the line. Then here's the formula for B1. Again, what else is there to tell you? Plug into this formula from all the quantities we calculated earlier. You do that, you get this. And then the equation of the line is y hat equals this, the B1 goes in front of an x. So then put x plus this number. Okay, so it's y hat equals this times x plus this. And that's the equation of the line that's as close as possible to the data. That's what it says here. The equation of the line is y hat equals b1x plus b0. Put the b1 and the b0 in. There's the equation of the line that's as close as possible to the data. Before we get to part C, here's just a picture of the scatter plot, and then here's a picture of the line whose equation we just found. That apparently is the line that's as close as possible to all the data points. That means if you draw any other line besides this one and calculate the total error, it'll have more total error than this line will. This line has the smallest total error, so it's closest to the data. So that's the line equation we want to use when we make a prediction. So now part C said, predict the outside temperature if the average temperature of the Earth if the carbon dioxide level reaches 400 parts per million. So the whole point is to make a prediction. So when they ask you to make a prediction, they're asking you to predict the outside temperature, and they're asking you to predict y. We're always going to predict y, but they're going to give you x. So it says when the carbon dioxide level reaches 400 parts per million, that's x. They're giving you x. They want you to predict y. What do? You just plug that in to x in the equation of your line. Okay, so you just plug it in. So if you change the x to 400, you get that. Calculate that, and that's your guess for the average temperature of the Earth. So if the carbon dioxide level gets to 400, then I predict the temperature of the Earth is going to be 14.843. Just plug in the 400 here, calculate, and you get your prediction for y. So we call it y hat. That's your prediction for y. That's your best one number guess. All right, questions so far? Okay. One thing to tell you, whenever they ask you to make a prediction, they're going to have to give you the x because they're asking you to predict y. They're going to have to tell you what the x is. And just so you know, the x that they gave you in this problem, they gave you x is 400. It's called x0. The reason I'm telling you that is because x0 is going to show up in a formula in a minute. So when you see an x0, that's the x that they gave you when they asked you to make a prediction. Okay, so the 400 is the x0 is basically what I'm saying. Okay, so now this is a one number guess for the average temperature of the Earth. We don't like one number guesses. We want to build an interval around it. So that's what part D says. Part D asked us to build a 90% prediction interval. So we need to find the margin of error. And we're going to add and subtract it from this to get our interval. But in order to find the margin of error, we got to find these things first. We got to find T alpha over 2, and we got to find SE. Let me just remind you real quick how to find T alpha over 2. So this is just taking you back to section 9.2, I think. Anyway, how do you find T alpha over 2? First thing you do is you write down that alpha is 1 minus the confidence level. The confidence level in this problem was 90%. It said it on the previous slide, 90% prediction interval. If you write it as a decimal, it's 0.90. So 1 minus 0.90, you get 0.10. So you get alpha. Then you divide it by 2. You always divide by 2. So 0.10 divided by 2 is 0.05. Then you're going to need the degrees of freedom. The formula is n minus 2. Remember, n is 10. It's how many pairs of numbers we have. So degrees of freedom is 8. And then you're going to draw a picture. I didn't draw the picture here, so let me draw it now. I'm just trying to remind you how you'd find T alpha over 2's. So you draw the T distribution. T alpha over 2 is on the right side of the picture somewhere. So it's T alpha over 2, but since alpha over 2 is 0.05, we're looking for T 0.05. And I don't know the answer yet, but here's what I know. I know if you go from there up to the curve and shade to the right, area is the subscript. So that's how it worked back then in chapter 9. Okay, so T alpha over 2 is always on the number line on the bottom and on the right side of 0. And if you go up to the curve and shade the area to the right is just whatever the subscript is. And now you can look this number up in the table, in the T table. So we know the area in the right tail is 0.05 and degrees of freedom is 8. So we go to the T table. Area in the right tail, 0.05. Degrees of freedom is 8. You go like this and like this. And the answer is 1.860. Okay, so that's the number that goes here, 1.860. So you find T alpha over 2 first. Make sure you draw a picture. Okay, so you find T alpha over 2. So there's the answer. After you have T alpha over 2, then the next thing to do is to calculate this SE business, this standard error of estimate business. There's a formula for it. So you just plug into the formula. But let's talk about the formula for a second. So on top it says sum of y squared. That's something you calculated at the beginning. Sum of y is something else you calculate at the beginning. Sum of xy is something else you calculate at the beginning. B1, what that is, that's the number that's in front of the x in the equation of your line. This is B1 right here, the slope of the line basically. And B0 is this other number over here that's being added on at the end. So watch out for that. Okay, so this formula has B1 and B0 in it. Those are the two numbers in the equation of your line. Okay. Also, remember when you put things next to each other in math, it means multiply. So since B0 and this sum are next to each other, you have to multiply them together. So you do B0 times whatever sum of y answer was. Okay, and same thing here, B1, so you do that times whatever the answer to sum of xy was. Again, n is 10, so you put 10 down there. So the bottom will be 8. And another thing to tell you is sometimes when students calculate this SE, they get an error. If that ever happens to you, let me explain why that could be. Because I want you to notice, where'd it go? There's a minus here, but sometimes B0 is a minus as well. So if B0 is a negative, then there's double negative going on there. What you need to do is you need to erase them, make it positive. You know, two negatives next to each other means positive. If you don't cancel out the double negatives and make it a positive, you might end up with a negative and a square root accidentally, and you can't take a square root of a negative, so your calculator will say error. So watch out for that. Same thing over here, B1 is negative, and there's already a minus in front of that. You need to cancel out those negatives. Okay, if you don't cancel them out, you'll either get the wrong answer or your calculator will say error. But other than that, all you do is you fill into this formula. So here I'm going to fill it in. Okay, with the numbers we calculated earlier, plus the B0 and the B1. And when you calculate it in this problem, you get 0.347. Now, after you have that, now we can calculate the margin of error. Here's the margin of error formula. T alpha over 2 is this. SE is this. You're going to multiply those. Then you're going to multiply by this root. And again, you just fill into this root. N we know is 8. X bar, sum of x squared, and sum of x are things we calculated at the start of the problem. And then there's the x0 that we talked about. Remember what that is. When they ask you to make a prediction, they're going to give you an x. The x they give you is x0. So x0 in this problem is 400. They said when the carbon dioxide level gets to 400, like they're giving you x is 400, predict the y. So that's what the x0 is over there. And you just fill in again. See, x0, 400. And you just fill it all in. When you're done and you calculate it, you multiply all this stuff together. My advice to you would be to calculate this mess first, get the answer, and then multiply by each of these things. When you're done, you get this for the margin of error. And now we can finally build our interval. So how do you build the interval? You take your best one number guess for y, and you add and subtract the 0.970, the margin of error. So the 90% prediction interval, again, you just do y hat minus this and y hat plus this. And put y in the middle. You're saying, I think the average temperature of the Earth is somewhere between these numbers. And there is the prediction interval for this problem. So that's how these kind of problems go. They're all just like that. Okay, just a lot of formulas to fill in and all that stuff. A lot of tedious calculations. But as far as the idea goes, it should be pretty simple. And there, right there, is a summary of everything we did in this problem. Any questions? Okay, so since there's no more questions, we're done for today. Let me just say, since there's no more lectures or anything, it was a pleasure teaching you guys this semester. I hope you learned something. Hope you enjoyed it. I'm sure it was stressful because stats is a lot of work, a lot of stress. But I hope that you learned something from it, and it was worth it, kind of thing. Study super hard for the final, as I mentioned before. Take it seriously. Whatever difficulty level you expect it to be, expect it to be more. That way you're super prepared when you go into it. I'd rather you go into the final over prepared and go, oh, this is easy, as opposed to being under prepared and like, oh my God, what do I do? And freak out and like blank out, kind of thing. So good luck on the final, crush the final. And that's pretty much it.